This is the video for the AP exam questions for the Chapter 20 review. So let's get to it. The first one says we have two half reactions. We have copper being reduced. We have chromium being reduced down to chromium 2+, along with their standard reduction potentials. According to the half reactions represented above, which of the following occurs in aqueous solutions under standard conditions? Essentially, what we're saying is which one of these will be reduced, which one of these will be oxidized, and then how would we write the equation to represent that. As you see, the copper has a higher reduction potential. This number is higher. This means copper is more likely to be reduced. Chromium has a lower reduction potential. So copper will be reduced and chromium will be oxidized. Now the way these reactions are always written in the reduction potentials table is being reduced. Notice chromium is going from +3, plus an electron, being reduced, down to a +2. So what you'll have to do when you write the actual reaction is to flip this. And as we flip it, you'll end up chromium 3+ on the right, chromium 2+ on the left. So chromium 3+ should be on the right, which means this one's out because chromium 3+ is on the left still. This one's also out. We're looking for chromium 3+ on the right. This one's out. And this one's out. So what we have left with us is showing chromium 3+ on the right, chromium 2+ on the left. Chromium 2+ on the left. We show chromium being oxidized. We show copper being reduced. And notice it's also balanced because we have 2 electrons here. In order to balance them together, you have to multiply this half reaction also by 2. And that is lined up with the 2 and the 2 on the chromium. So this is the correct answer, part B. Take a look at the second question. Too far. Down we go. Apologize there. Okay. When a magnesium wire is dipped into a solution of lead 2 nitrate, a black deposit forms on the wire. So we have a beaker. This is lead 2 nitrate. And a magnesium wire is dipped in. And all of a sudden, it gets coated with some black stuff. Essentially, we're saying a reaction occurs. Which of the following can be concluded from the observation? A says the standard reduction potential for lead is greater than that for magnesium. What we're saying is that lead is more likely to be reduced, which is, in a way, saying that lead is less reactive than magnesium. Now, this is actually true. We know that lead is less active. We know magnesium is one of the more reactive metals because it comes from the S block. And when magnesium reacts, it oxidizes. So lead will get reduced. So this is actually the correct answer. Let's take a look at the other ones and see why they are not the correct answers. B says magnesium is less likely oxidized than lead. This is wrong. This is the opposite. Magnesium is more likely oxidized or more easily oxidized. C says an external source of potential must have been supplied. This is not true. If the external source were supplied, then the opposite reaction would occur. The lead would actually get oxidized and the magnesium would get reduced. So this one's out. The magnesium wire will be the cathode. Again, this is wrong because oxidation occurs. We see that magnesium has to get oxidized. If magnesium gets oxidized, that's happening at the anode. Oxidation, remember, happens at the anode. So that one's out. Lead solid can spontaneously displace magnesium. This is also incorrect from solution. And this is the opposite is actually happening, or you could say magnesium is actually forming in solution. The lead is actually depositing. So in truth, it is lead that's depositing on the magnesium surface, but it's not displacing magnesium 2+ from solution. Is actually displacing magnesium 2+. I'm sorry, it's displacing magnesium metal, magnesium solid. That one's out. So hopefully that one made sense. Apologize for the slight confusion. Let's take a look at the next one. So the next one here is actually 3 questions in one. So we have a half cell, and we have 3 half cells, and then we'll be asked some questions about these 3 half cells. The first half cell contains aluminum and copper. The second one, aluminum, iron. The third one, iron and copper. And all of them are under standard conditions. Notice everything is in a 1 molar solution. We're also given the cell potential of the whole reaction. And 3 asks, what is the standard cell potential of galvanic cell Z? Now, this here, this cell, the last one, is actually, if you take a look, can be obtained by rearranging the first 2 cells. This is allowed, just like Hess's law allowed us to do. What you could do is you can move aluminum from the left side to the right side, and it'll cancel out. You'll be left with copper, 2+, and you'll be left with iron, 2+ on the right. So let's go ahead and do that. Let's go ahead and move, if we move this over, or if we flip it, and actually, let's go ahead and rewrite so it's a little easier to see. Let me go ahead and rewrite it flipped. So we have 2Al plus 3 on the left side. You have 3 iron on the left side. And then you have aluminum on the right side and 3 iron, 2+ on the right side. What you'll see happening now is that the aluminum 3+ will cancel out with this aluminum. The aluminum, regular aluminum, will cancel out with this regular aluminum. I forgot a 2 in here. The irons then will stay. So, by the way, this one's out. A little easier to see. And what you'll see is that you have iron on the left side. You have iron 2+ on the right side. You have copper on the right side. And you have copper 2+ on the left side. Now, one thing before we put this together, because we flipped it, anytime you flip a reaction, your cell potential becomes negative. So this now reverses. This was also true of Hess's law. But the difference between this and Hess's law is that we don't care about the 3. We don't have to divide the whole reaction by 3 and then divide the E cell by 3. This is because voltage is an intensive property. We've mentioned this a few times. So, intensive property, which means the amount doesn't matter. It's like density, which means we can simply put these 2 together. So 2 minus 1.22 is 0.78. So really we're applying Hess's law to this problem. All right, let's go ahead and see what number 4 tells us. In galvanic cell Y and Z, let's pull it up just a bit. Which of the following takes place in half cell 3? So what we're asking about is 3, and both of these contain the same chemical. So 3 actually refers to, in this case, iron. So cell 3 is actually iron, and if you take a look above, it tells you that iron. So what we've got is we've got iron being reduced. Notice iron is going from a +2 down to a 0. So iron is being reduced in cell Y, and iron is being oxidized from a 0 to a +2 in cell Z. So that one's a simple one. Reduction occurs in cell Y and oxidation in cell Z. So part C. And the last one says if the half cell containing 1 molar iron nitrate in Y and Z is replaced with a half cell containing 5 molar iron nitrate, what will be the effect on the voltage of the 2 galvanic cells? So anytime you increase the concentration, what you're doing is you're applying this equation, minus 0.059 over n log of Q. Remember, this is the equation to determine the voltage under non-standard conditions, this E. Now, because we are increasing the molarity, that affects Q. Remember, Q is products over reactants. We're increasing the molarity of iron. Now, in cell Y, notice the molarity of iron is increased. Iron is a reactant, which means the bottom here increases, which means this ratio becomes smaller, and the log of a small number is negative. This becomes negative, which means you subtract the negative, and your voltage, your E, goes up, because it becomes more positive, goes up. So the voltage increases in cell Y. We'll put that here. The opposite occurs in cell Z, because iron is a product. Because iron is a product, your ratio of product over reactant, the number gets bigger, then your Q, your ratio, is a bigger number. The log of a big number is positive. You end up subtracting a positive. Your voltage goes down. So it decreases here. So the voltage will increase in Y and decrease in Z, and that is C. So essentially we're just applying, this is the Nernst equation to our half cells. So hopefully that was it for this lesson. All right, so think through them and make sure you understand what these concepts are referring to.